So we just went through and calculated the pH of a buffer that contains equal molar amounts of acetic acid and its conjugate base from sodium acetate. The pH of that buffer was set 4.74. We just went through that and also figured out that when we added a little bit of solid sodium hydroxide to that, we added a strong base to it, we saw that the pH increased slightly to 4.78. So now we're going to do the complement to that, and we're going to say, let's imagine that we start with that same buffer solution and don't add a strong base, we add a strong acid and see what happens. I'm going to go through this problem fairly quickly with not a lot of deep explanation because I'm going to assume that you've already watched the videos on parts A and B. Part A, again, to understand how a buffer works and how we got pH 7.4. And then part B, when we went through this problem and saw what happened when we added sodium hydroxide to it. So it's going to parallel what we saw with part B very greatly. But again, I'm going to go through it in a little bit quicker fashion than I had for part B. All right. So again, part C, we're going to treat this the same. We're going to say who's in solution. So we've got our weak acid, 0.5 molar, and 1 liter of it. We know from our calculations that this equals 0.5 moles of our weak acid. We've got our sodium acetate, again 0.5 molar, 1 liter, and that means we have 0.5 moles. We have some sodium that we had from our sodium acetate, but we don't consider the contribution of sodium, so we won't write that in any of our equations. But we also have chloride ion, which is another counter ion that comes from the HCl. And as we see here, HCl is really H plus and Cl minus. So if we had H plus or HCl that we added, right, here's the question from this. We've added HCl. HCl is really H plus and Cl minus. There's no HCl together because it's a strong acid and it completely dissociates. So what we do need to consider is that we've got H plus ions in solution, and we have 0.02 moles of that. So looking at who is in solution and who is not a spectator ion, we've got a weak acid, its conjugate base, and then H plus in solution. The only combination that chemistry can happen with is a weak base and H plus. You're never going to have two acids that are going to react with one another here, especially when you have a conjugate base that's available. So let's write the chemistry that's available. We start with the molecule that would react with the strong acid, and the strong acid again is just H plus. Chemistry is one-way arrow, and we make our weak acid here. ICF table, 0.5 moles of each of these guys to start, and 0.02 moles of our strong acid. This guy being our limiting reagent means we use up all of it, and we're going to use up the same amount of our conjugate base and generate the same amount of our weak acid. We end up then having 0.48, 0.52, and our limiting reactant gets used up. You might get confused a little bit in first and say, well, wait a minute, those are the exact same numbers that I got for part B. But if I put part B up here for a minute to take a look at this, yes, we did get 0.48, but that was the concentration that was left of our weak acid. Now this is the amount that's left of our conjugate base. And that's because the strong acid that's added reacts not with our weak acid, the strong acid reacts with our conjugate base. So that army is deplenished a little bit, and we supplement that of our weak acid. So same numbers, but those numbers belong to different molecules. Just like we saw before, we're going to assume no volume changes. And so that means our volume is 1 liter. So if we figure out our new concentrations of species, we've got 0.52 moles. Here's our weak acid. 0.52 moles of that per liter is 0.52 molar. Our acetate ion is 0.48 moles per liter, 0.48 molar. So those are our new concentrations of species. If we think about the equilibrium that exists between them, it's going to be the same equilibrium that I wrote for part B. So I'll propagate this table and then we'll see how this is different. Okay, so again, if I look at how this table is different from what we had in part B here, same equation, but again, this is now going to be 0.52, because when we added a strong acid, we're actually going to make more of our acetic acid molecules. So table looks very similar, but it's kind of taken it in the other direction, and that we're supplementing the amount of weak acid and depleting the amount of conjugate base. So going through and again propagating this using our Ka values, we're going to have X 0.48, doing our assumptions, 0.52. We're going to solve for X here. I shouldn't say this is equal to X. We're going to propagate this and we're going to solve for X. So X in this case is going to be equal to 2.0 times 10 to the minus fifth. And that's equal to our H3O plus concentration. So the negative log of 2 times 10 to the minus fifth pH will equal to 4.70. Again, that should be expected. If we think about what happened here, we started by having an equal army of conjugate base and weak acid. When you add a strong acid to it, the chemistry that happens is you deplete your conjugate base army. Just by a little bit, you supplement your weak acid army. And so in doing that, that again is going to allow us to decrease the pH slightly. Again, that might make a little bit more sense when we solve this using the Henderson-Hasselbalch equation. So pH equals pKa plus the log of the conjugate base over the weak acid. So negative log of 1.8 times 10 to the minus fifth plus log of 0.48 over 0.52. Right, our conjugate base is now a smaller number than our weak acid. And if we again compare this to part B, we can see what we have here in our last part. Now we have the log of a number that's less than 1. Log of a number that's less than 1 is negative, which means this is going to contribute to dropping the pH. Mathematically, this will still get us to the same 4.70 value. So kind of wrapping up and summarizing here, we had 3 different situations, right? We had a buffer solution that we figured out the pH, no chemistry going on. We used an ICE table, solve for X, or use the Henderson-Hasselbalch equation to get a pH of 4.74. Part B added some solid sodium hydroxide. When you add sodium hydroxide, that depletes your weak acid, supplements your conjugate base. That slight shift in the ratio between those is enough to slightly increase your pH. And then again, that increased to 4.78. The last part that we did here, part C, we added some HCl, strong acid. As we can see here, when we propagated both our chemistry and our ICE tables, we can see that the pH is going to slightly decrease because we've depleted our conjugate base army and we've supplemented that of our weak acid. So again, this one ends up being 4.70. And not surprisingly, the same amounts of strong base and strong acid resulted in a increase of 0.04 units or a decrease of 0.04 units. So what we'll see is we get to sample problem 19.4, which is kind of our monster titration problem. And then we did some in-class problems also dealing with titrations, is what we'll see is that we're going to do very similar chemistry. What's really going to change when we do those is the fact that volume changes are now going to become significant. But these problems will be exactly the same. We'll have this chemistry that happens, but again, we're going to have to consider the fact that our strong acid or strong base gets added from a burette that has volume. And so we needed to consider what those volume changes are. But other than that, these problems are going to be exactly the same.